So to begin with, let's start with a prayer. Asatoma Sadgamaya, Tamasoma Jyotirgamaya, Mrityoma Amrutam Gamaya, Om Shanti Shanti. This prayer invokes God to take us from untruth to truth, from darkness to the light, from death to immortality, and let there be peace, peace, peace. Thank you, one and all. Before we start with the session, I have some instructions to be followed by the participants. I kindly request all the participants to log in into the Zoom platform using the correct name or using their mail ID. If you have any queries regarding the session, please drop your queries in the chat box. All the questions will be answered at the end of the talk. At the end of the session, a feedback form will be shared in the chat box. Thank you, participants. Hope you have a good time. Now I welcome Dr. Babita B., Head of the Department MLAC, to give an overview of today's session. Welcome you, ma'am.
Good morning to one and all, to the distinguished speaker, to the organizing team of ICTS and MLAC, and to all the dear participants. Today, actually, I'm going to give you an overview of today's talk. MLAC, a college with history of more than 40 decades, vibrantly stand in the heart of the city, is among the top 50 all India level and top 10 colleges in Bangalore as surveyed by Nielsen India Today. MLAC is one such institution which is a demand-driven, value-added undergraduate, postgraduate programs, diploma and certificate programs in disciplines of arts, science, commerce, management, and computer application. The college have already been credited with various achievements. To name a few, college with potential for excellence by CPE Phase 2 by UGC, star status by DBT, Government of India, and many grants from DBT, DST, FIST, UGC, BSR, ICSSR, and so forth. The alumni from MLAC have been placed in top position in various organizations, academia, and industry, and constantly the MLAC have been working together in collaboration with the industry, internship, and research projects. So this is about a brief overview about MLAC. About ICTS, now International Center for Theoretical Science, ICTS of Tata Institute of Fundamental Research, which was established in the year 2007, is a interdisciplinary center with three major goals. The various programs, what they offer, which are unique, the research objectives, what they render, and various outreach programs, what they put forth. And one such program, outreach program, is this Einstein lecture. ICTS public lecture series initiated as part of the centenary celebration of Albert Einstein's general theory of relativity. Educational institutions and other public organizations from all over India are invited to partner with ICTS in organizing public lectures at various venues in India. So we from MLAC, we are profoundly honored to have ICTS in this platform, and we are also indebted to have our distinguished speaker to deliver the lecture. So I hope today all of you will have a fruitful time in enriching a knowledge experience venue. I put the next session to Ranjita now. Ranjita, you can take over.
Thank you, Babita ma'am. Now welcome Shashikala, Principal of MLAC, to address the gathering.
Yeah, a very good morning and greetings from MBlack to one and all present here. We live in a world of science in which science from physics and mathematics through biology and computer science affects us all in day-to-day life. In this context, International Center for Theoretical Science, TIFR, has achieved some measures of success by integrating the knowledge of human values. I'm delighted to acknowledge the efforts of Einstein Lecture Series, spreading their tentacles across, and I welcome ICT organizing team for taking this initiative. I wish to welcome Dr. Vijaykumar Krishnamurthy, the speaker of today's program, who will highlight the importance of physics and provide a glimpse of fascinating physics found in living system, physics of life. I welcome all the delegates, research scholars, and enthusiastic students to this web-based seminar. Thanks to technology for bringing together all of us in the same platform across globe. I welcome all the MLAC faculties and congratulate the Department of Biotechnology for coordinating this event. I wish all the participants a very successful event. I hope all the participants will have a carry home message. Thanks to one and all present here. Thank you, sir.
Thank you, Sashikala ma'am. Now I request Ms. Archana Preeta to introduce the speaker, Dr. Vijaykumar Krishnamurthy. Over to you, Archana ma'am.
Thank you, Ranjita. So it's a pleasure to introduce the speaker for the day. So Dr. Vijay studied for his BSc in MES College, Bengaluru, and obtained a PhD in physics from the Indian Institute of Science. Spent a couple of years as a postdoc at the Max Planck Institute for the Physical of Complex Systems and Molecular Cell Biology and Genetics in Germany, and returned to India a few years later to join the faculty of the International Center for Theoretical Sciences, ICTS-TIFR. He never liked biology in school and left it as soon as possible it could be. The non-formal science education programs at the JN Planetarium in Bengaluru strengthened his foundations in physics and mathematics during his undergraduate days. A PhD on the physics for life, which he is pursuing at the ICTS and plans to do so for the foreseen future, is what we see. So to brief up, Dr. Vijay is a man, simple man with knowledge and wisdom. Thank you, sir. I welcome you to the talk, and the stage is yours, sir.
Thank you very much. Can I share my screen?
Thank you, Archana ma'am. Yes, sir.
Okay, so is this visible? Can somebody confirm?
Yes, sir, it's visible. Your PPT is visible.
Thank you. Thanks everyone for coming. Thanks MLAC for joining this venture. I wish I could have actually come to the college in person, but the situation being so doesn't permit one to do that. But I have passed in front of MLAC many a times during my undergraduate days. As was just mentioned, I did my BSc in MES College, so MLAC is just on the way to MES College. Nevertheless, another time. So to get ahead with the talk for today, so I'll be speaking about the physics of life. I'm at the International Center for Theoretical Sciences, the Tata Institute of Fundamental Research. So I will go slow, and the first part of the talk will probably be more familiar to physics people who have a physics background. I request people with a biology background to sort of bear with me. Maybe the second half of the talk will be familiar to the biology background people, but the physics people may or may not have seen those things. So my hope is that by introducing this physical way of looking at matter, and I hope that I can actually give you a feel for the kind of things which are really, really fascinating in the physics of living systems. So let's jump ahead. So I'll go very broadly. And I start with a very, very broad question. So these are typically the questions that come up in trying to understand science. So you ask questions like, what is the world made of? And so there's this question, answer of trying to understand the scales at various levels. So you start from a human level, you go down, you have solids, atoms, cells, molecules, atoms, and quarks, and so on and so forth. You go up, there are planets and stars and galaxies and whatnot. So this is trying to understand structure. This is trying to find out where is what at which level. I'm just showing you the spatial scales. Along with this also comes the temporal scales. There's another question that one can ask, and you ask, how is the world put together? Now, what do we mean by this? So the idea is that if I give you a bunch of interacting units, I'll clarify this in the next slide, and I tell you the kind of forces that act between those units, basically the interactions, how do I build the next level? This is a very hard question. You'll realize the complexity of this question, and in particular, the complexity of this question as applied to living systems as we go through. So to elaborate this question, how is the world put together? So the idea is that if I give you a bunch of nucleons, how do you construct a nucleus? A nucleus is basically a many-body system of nucleons. So if you go up, how do you construct an elastic solid given a bunch of atoms and the interactions between the atoms? Or if I give you electrons and ions, how do you construct a metal and show that it actually conducts electricity? If I give you a bunch of complex molecules, how do you build a cell? Or maybe a bunch of living things put together, how do you build an ecosystem? Or to go to the higher scales, how do you build a galaxy given a bunch of stars? So there is a different question being asked here. The one question is to find out what is where at which level. The other question is, I give you something at one level, build me the structure at the next level. That is a hard question. So this really boils down to this two viewpoints that one has in trying to understand science. I very strongly encourage you to read this article by Phil Anderson, which appeared in Science in 1972. It's really a very deep article on trying to understand the various ways of looking at science and doing science. So the basic construct here is trying to understand the reductionist view of science versus the constructionist view of science. So I'll make these things clear as we go along, but I want you to read a couple of passages from this paper, a very deep paper. So one of the passages says, the reductionist hypothesis does not by any means imply a constructionist one, in the sense that the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. He goes on to explain that if you put a large number of complex aggregates of elementary particles, so I quote him, the behavior of large and complex aggregates of elementary particles, it turns out, is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear. And the understanding of new behaviors requires research, which I think is as fundamental in its nature as any other. So the points to note are the following, that just because you know some fundamental laws does not mean you understand the universe at the next level. So the ability to know what is there at which level and how the tiny things interact with it does not mean you can go the reverse way and explain the higher up levels. So at each level, new complexity comes up. And the complexity actually leads to new properties, which are really emergent properties, which don't exist for the single unit of that system, which really are a collective quantity. And so this kind of a research is really not applied. I mean, that's one of the things that Anderson makes a very strong case for. And it's really as fundamental as it can be, because what is fundamental depends on the level that you're looking at. And so at the level that you're looking at, the laws that are appearing here are fundamental at that. So the way we understand, therefore, the emergent properties of interacting many-body systems is trying to understand, for instance, you put a bunch of electrons and ions to form a metal, or you put a bunch of molecules together to form a liquid. So there are certain properties of the metal and the molecules in a liquid which sort of emerge when you put a large number of them together. They don't exist for individual units. They are attributes that exist only for a many-body system, and they do not exist for one or few bodies. So some examples. Think of viscosity of liquids, for instance. If you think of viscosity of liquids, a single molecule of water does not have viscosity. When the property really is an emergent quantity, and the emergent quantity comes up when you put a large number of water molecules together. It's really this emergence that one is trying to understand. And so a property like viscosity, or many of these kinetic coefficients like elasticity, viscosity, conductivities, and these are really things that emerge when you put a large number of units together. Single units do not have them, collective units have. That's a different way of looking at things, right? So it's saying that just because I know the individual units and the interactions between them, this statement is making the case that you really don't know what are the emergent properties there and what are the emergent behaviors that come up at that level. So there's no way to predict them from ab initio calculations. So what one is trying to understand is that there are collective states of interacting units, and these are what are called the phases of matter. Right? So the phases of matter, to understand them, we first need to understand how do you understand the physics of a bunch of interacting many particle systems. This is something that one learns in undergraduate classes, basic ideas of thermodynamics. So as most of you would know, that if I take isolated system, say a bottle of water, which is closed and has a thermal insulation, and I leave it there for some time. I leave it for a long time. I don't slosh it. I don't touch it. I don't heat it. I don't do any perturbations to the system. I look at a small volume inside the water bottle, and I look at the properties of the molecules inside that small volume. So it turns out that one can actually do what is called thermodynamics. So this is the great achievement of physics in the 19th century. We understand how to predict the macroscopic properties of these aggregates of simple interacting units. So the idea is that there are certain quantities like the free energy, which free energy depends on the context that you're looking at. And the equilibrium state of a system is really a state which minimizes the free energy of the system. So this is the basic idea of thermodynamics that one brings into the picture, that you're really not looking at individual particles, not the motion of individual particles, but really looking at statistical properties of a large number of them. And there are certain newer things that come up and certain newer laws, for example, the minimization of free energy. The minimization of free energy also tells you that at given external conditions, constant temperature, given pressure, given volume, what is the phase which minimizes the free energy? And so therefore, what is the equilibrium phase? So this is what we'll turn to next. By the way, there is a microscopic basis for thermodynamics, and at equilibrium, for systems which are at equilibrium, this is the idea of equilibrium statistical mechanics. I mentioned that phases of matter are basically collective states of many particle systems. An interesting thing is that the chemical composition is the same. It's really the way you put together different units in certain fashions that gives you these attributes of the state. So here's a picture that shows you rapidly melting argon, and you can simultaneously see the solid, liquid, and the gas phases in the same picture. So a familiar picture that we all understand is the pressure temperature phase diagram, in which you look at the possible phases at a given value of pressure and temperature. And like we sort of intuitively know, there are these three phases for simple liquids, like the solid phase, the liquid phase, and the vapor phase. So this is something very familiar for us in our day-to-day life, right? So if you take something in the solid phase and you heat it, it goes to the liquid phase, and then eventually it goes to the vapor phase. A kitchen experiment that every one of us can do. Take a bunch of ice cubes, put them on a stove, heat them up, you form a liquid, and if you heat it more, the liquid evaporates, and finally you get the gas phase. So this is a familiar picture that we all see in our everyday life. This is basically a phase transition that's happening. There was a solid phase, you heated the system, it went into the liquid phase, you heated further, went into the vapor phase. But then we also know, and we learn from chemistry classes, that there are certain ways in which the atoms and molecules constituting the phase are arranged in a solid, liquid, and a gas. In a solid, they form a very nice crystalline array, very ordered, periodic, regular structures. In a liquid, they are less ordered. There's some small range order, but they're much less ordered compared to the crystalline phase. In a gas or a vapor phase, they're really disordered. I mean, there's hardly any order characterizing the molecules staying close to each other and so on. But this is all words. So how do we actually measure something? How do we characterize order? And how do we construct a quantity which is experimentally measurable, and for which we can also write theories, and so therefore can gain further understanding of how the phase of the system looks like. So let's say you have 5 atoms. I'll use interchangeably atoms and molecules or units. Let's say if we have 5 atoms sitting there. So one way to characterize order is to look at all the pairwise distances. So you look at every pair. So if we have n atoms, there are n choose 2 pairs. So n combination to n to nc2 pairs. And so therefore you have nc2 number of distances. So you can ask, what is the frequency of these pairwise distances? So I chose 5 to illustrate the idea of the pairwise distances. N is typically of the order of Avogadro number, as you all know. So this idea of trying to measure the frequency of pairwise distances is what's called the pair distribution function. And this function really gives you an idea of how the structure of the system really looks like. So I really want you to think about this for a minute or two, and you will really understand how to think about this in a very qualitative manner without requiring too much of physics and mathematics. In the vapor phase, we know that the vapor phase is very low density. There are very rare collisions. Atoms hardly meet each other. They're just moving in straight lines. And so therefore, if you ask what is the frequency of finding a certain distance between pairs of atoms, well, the atoms can't go through each other. So therefore, for all distances which is less than the diameter of the atoms, the pair distribution function would be 0. But for all distances larger than the diameter of the atoms, well, they are equally likely to be found anywhere. So the pair distribution function is 0 for distances less than the diameter and is some constant value for distances beyond the diameter. So it's a boring state. If you go to a liquid, you all know that the density goes up. There is moderate density. There are frequent collisions now. I mean, they're not as rare in the vapor. Atoms do bump into each other every now and then. So therefore, if you ask for the pair distribution function, this structure, the short range correlations, the moderate density, the frequent collisions, all these comes up in a certain structure that the pair distribution function shows. So you actually see that there is, again, nothing below distances less than the diameter. Surely you can't go through the atoms here too. But then you don't see any no longer a flat profile of the probability, but you see certain peaks coming up. Something that one would have learned in chemistry. These are the solvation shells that one thinks about. So you see enhanced probability, enhanced frequency of finding the pairs at a distance slightly above the diameter, and there's a dip, and then one more peak, a dip, and so on. And eventually it goes into something which approaches the gas phase. The other extreme is the solid, the crystal. Here you see the atoms are really arranged in a very, very, very crystalline fashion, a very regular fashion. And so therefore, if you really ask what is the probability of finding pairwise distances, they're very sharp values because the atoms hardly move around. They're almost frozen in their positions. And as such, you find that the pairwise distances between the atoms can only take on certain sharp values. And so you see these sharp peaks in the pair distribution function. So this is the way one tries to characterize order. So the point is that the knowledge of the pair distribution function really reflects the internal arrangement of the phase that is going on. This is something that can be measured in experiments. And that's why it's useful to think about this and to calculate this. For example, if you do scattering, X-rays, for instance, X-ray diffraction measurements can measure a Fourier transform of the pair distribution function. So that's about the static structure. But how do we understand these phases from some interactions? I mean, that's the basic idea that we wanted to think about, that if I give you a bunch of units which are interacting, and I tell you the kind of interaction that is there between the units, how do I understand the possible phases that the macroscopic aggregate of the system can display? So the point here is to understand a typical potential energy between two neutral atoms. The atoms are not charged, so there are no Coulombic interactions. So if you think of a typical potential energy profile, the structure looks like the green curve shown in the graph. How do we understand this? Well, surely there is short-range repulsion, in the sense that if you try to bring the atoms too close together, there's going to be electron cloud repulsion, the nuclei are going to see each other, and so they'll be pushed apart. So it's basically the statement the atoms can't go through each other. But then if you get them far away, though they are neutral, they are going to have an effective attractive interaction. This is van der Waals forces, dipole interactions, these fluctuation-induced forces. So the typical potential between any two neutral atoms or molecules is the green curve that is shown there. There's a long-range attraction and there's a short-range repulsion. So this general idea, the details of the curve do not matter. This general idea of having a short-range repulsion and the long-range attraction is enough to tell you qualitatively where each phase occurs when compared to certain energy scale. The question now is, what is the energy scale? So you see from the graph there is a certain depth of the potential. So first of all, the potential goes to 0 or some constant value far away, and compared to that far away value, there is a depth. There is the attractive potential, the depth of the attractive potential. So that gives you some energy scale, some typical potential energy of attraction between the atoms. You also know that when you're looking at a macroscopic system, you're controlling, for instance, the temperature of the system, which is basically the average kinetic energy of the system. So compared to where the temperature lies with respect to this graph is where you get the different phases. So how do we understand that? So look at a case when the temperature is much, much higher compared to this attractive depth. So then you're basically looking at the case where the atoms don't see each other at all. I mean, the attractive interactions between the atoms hardly matter. The atoms come and bump into each other so fast, driven by their kinetic energy, they hardly see the attractive potential. It's almost like billiard balls or tennis balls coming and bumping into each other and going back. So that's where you get essentially the vapor phase, because you're not even giving enough time for the atoms to sample the attractive potential, and so sort of get locked. in an attractive pair. So that's what gives you the vapor phase or the gas phase. The next case is when the temperature, or the energy associated with the temperature, is comparable to the potential depth. And that's essentially the phase where you get liquids. So the temperature is not so high that the atoms will actually come and hit and go away, unlike the vapor phase. But it's also not so low that when the atoms come and hit each other, they'll get stuck and form a bound state. It's sort of in between the two things. So a comparison between the thermal energy scale and the potential energy depth of attraction, when the energies match, that's when you get this liquid phase. So there is short range ordering, not too long range, but then the atoms are also not so sparse as in the vapor phase. The extreme case is that of the solid. So here you have a temperature which is far below the potential energy depth for the attractive well. And so therefore, temperature hardly does anything. I mean, the atoms are basically stuck in the attractive well of each other. And so you get a very nice crystalline ordered phase. So this is the way to think about the idea. A detailed calculation would require you to do a statistical mechanical calculation, which involves a lot of mathematics, but there is a very nice hand-waving way to understand, compared to this potential well, which has a short-range repulsion and a long-range attraction, comparing that with temperature tells you how to think about the gas phase, the liquid phase, and the solid phase. But then these are static pictures. I mean, I've drawn a bunch of atoms in the vapor phase or in the solid phase, and they're just sitting there in the picture. But that's not what the atoms do, right? I mean, they actually move around. Even in the solid phase, the atoms are jiggling around. In a vapor phase, definitely they're going around in straight lines and hitting each other very rarely. So if you really look at the molecules, they're not stationary. I mean, in fact, if you look at the temporal trajectory of one of these molecules, you catch hold one of them and say, let's say you could attach some probe into that and could see it through a microscope, you'll see a typical trajectory like those shown in the three phases. In the vapor phase, the molecules hardly hit each other. They just go in straight lines. Maybe once in a while they bump into somebody, or they mostly bump into the walls of the container and they come back. So it's mostly straight lines, long straight lines, punctuated by scattering trajectories here and there. In the liquid case, the collisions are much more frequent. So they're going to bump into each other much more often. So therefore, you see this jagged path that comes up. So the typical distance traveled by the atom before it encounters another neighbor and gets scattered is much shorter compared to the vapor phase. So the trajectory, the straight line trajectories are far shorter. And so what you get is a very random jagged path. So this is essentially the Brownian motion that we all know. In the solid, you have the other extreme case that the positions are more or less locked in, yet the atoms can actually vibrate just a little bit about their mean position. They really can't leave the mean position on short time scales. And so they're more or less stuck in those positions. So what I want to do is to connect this idea, this intuitive idea that we have of molecules just moving straight lines in vapors and hitting each other more frequently in liquids, and in solids just jiggling around their mean positions, and try to see if I can make something quantitative out of it. So the idea is basically to measure the positions of the particles. So let's say you look at the positions at some times t1, t2, t3, you look at their positions, vectorial positions, from which you can figure out the mean position. So on the average, the particles go nowhere. I mean, there's no net drift on them. So a second quantity to look at to understand something about how the atoms actually spread out in time is what's called the mean square displacement. Here's a very easy way to understand this. So in high school, we learned that if you take an object and you throw it with a constant speed, then the distance from a given reference point increases linearly with time, right? So there are no other forces acting, no gravity, no friction, nothing. So I have an object which is moving with a straight line with a constant velocity. And so as you measure the distance of that object from some reference point, say at t equal to 0, the distance increases linearly with time. If that's the case, then the distance squared should go quadratically with time. So therefore, if we look at the vapor phase, you should really have a mean square displacement that goes t squared, that goes like a quadratic function of the time. On the other hand, in the liquid phase, the molecules bump into each other much, much often, and you will find that it can't go as fast as it could in the vapor phase. And so before it just tries to go straight, another guy comes and bumps and reverses the direction. And so you have a very jiggly motion. So it takes a little bit more math and some simple modeling to show that the mean square displacement at long times actually increases as a linear function of time. So the molecules are no longer going in a straight line, but they're really hitting into each other. And this hitting into each other really slows them down, makes them diffusive. On the other hand, in the solid, as we all understood, The molecules can't go anywhere on the average. They're more or less stuck around their mean position. They can just jiggle around here and there a little bit. And so therefore, if you look at the long time behavior of the mean square displacement, it does not depend on time. It reaches some constant value and saturates them. So the reason I wanted to emphasize these connections is to make this connection for equilibrium thermodynamics. So the way we understand the phases of matter in equilibrium thermodynamics is to appeal to the idea that there is a simple potential energy. You compare it with the typical energy that comes from temperature, the kBT, the average kinetic energy. If you compare that with the attractive potential, you get the three different phases. In the three different phases, there is a structural difference. The gas molecules can be found anywhere at any distance from each other, apart from being inside each other. In the liquid case, the yellow curve, you do develop some structure. A couple of peaks come up, but the peaks don't go far away. They die down very rapidly and approach the value of the gas. In the solid case, you develop sharp peaks because there is long range order, and you can see these sharp peaks as basically the specific values of the pairwise distance that you can see in the atoms. The dynamics is also something that captures this behavior. In the solid, the mean square displacement does not change with time. In the liquid, the mean square displacement increases linearly with time. In the gas phase, the mean square displacement increases quadratically with time. So in a sense, if the system is at equilibrium, knowing one typically tells you what is the other. So in the sense that one could look at a structure and guess that probably this is a solid. And if this is a solid, then you know how the mean square displacement looks like. And if the mean square displacement looks like, then you know how the structure looks like. And you know where in the phase diagram that one is. So for a system at equilibrium, I'm trying to emphasize that all these quantities are connected to each other. So there is a very nice connection that if you know one, you can really figure out what is going on in the other cases. This is for equilibrium thermodynamics. But then this equilibrium thermodynamics actually leads to the mechanical response of the condensed phases. So the condensed phases are the solid and the liquid. The gas is not a condensed phase. It spreads out if you open up the containing volume. So for the condensed phases, the properties that we just understood, mechanically, the mean square displacement, the forces, the various structures in terms of the pair distribution function, really tell you how the system behaves when you apply some force to it. So the idea being that if you take a solid, as you all know, and you shear it, well, it will respond to the shear by deforming. But then if you remove the shearing force, it goes back to its original position. This is the standard rubber band picture that we all have. Take a rubber band, stretch it, it stretches, leave the force, it goes back to its original position. On the other hand, for a liquid, I mean, this is an experiment you could do. Take a liquid in some glass, and you can shear it. And when you remove the shearing force, the liquid does not go back to its original position. The new position is as good as the old position. So there is no preferred positions for the liquid. And so therefore, the liquid just yields under a shearing stress and flows. So you capture this by saying that if you look at the stress, which is the internal forces generated in response to the shearing stress that you put. If you look at how the stress behaves as a function of the strain, for a typical Newtonian and Hookean solid, the stress is a linear function of the strain. On the other hand, for a liquid, the stress is a linear function of the strain rate, how fast that strain is changing. Not the strain itself, but how fast the strain is changing. For people who understand this, the stress is a function of the derivative of the strain, not the strain itself, temporal derivative. So that's the mechanical response. So this picture that we had was for simple materials, like you had a bunch of atoms. They were just basically points sitting here and there. But then if you really look around, even in your kitchen, in your bathroom, there are lots of materials which are not really made up of point particles. They have structure. One of the simplest structures that one can give is to make it an extended object. This is basically the idea of the liquid crystal. I mean, every one of us is using the ideas of liquid crystals right now. If you're seeing this talk using a laptop, mobile, desktop, whatever it be, the screen is made up of liquid crystals. What's called a liquid crystalline display, LCD TV. So this basically is the idea of trying to understand how to use these anisotropic materials to construct useful devices. But let's understand the physics. So the idea is the following, that I have an object which is now no longer a point. It's no longer a circle or a sphere, but it's really basically a rod. But then the rod does not have polarity. So, I mean, there's no head and tail, there's no sharp end and a pointed end or a flat end, but it's basically a rod which doesn't know its front and back, but it has an axis. So it is anisotropic. So I'd like to understand the kind of phases that this kind of a system can actually show. So if I just give you the center of masses of a bunch of particles, again, like in a liquid kind of a picture that I showed you earlier, you would probably say that these two center of masses, these two positions of the center of masses I'm showing, probably represent the same phase. That's true as far as the center of mass is concerned. But how about the following? Since these particles are actually things that have an orientation, I could have a phase in which the orientations are also at random, or I could have a phase in which the orientations are aligned on average in one direction. So the first phase is called the isotropic phase. The second phase is called the nematic phase. In the first phase, you don't have positional order, nothing like a crystalline phase. You don't have orientational order either. None of the particles are pointing along the same direction. They are pointing all over the place. In the nematic case, you don't have positional order. It's still a liquid as far as the positional degrees of freedom are concerned. But you do have an orientational order. So as far as the orientational degrees of freedom are concerned, it really looks like a crystal. So it's a liquid for it's a liquid for positional degrees of freedom. It's a solid for orientational degrees of freedom, hence liquid crystal. So these are not exotic objects or things that you would see in a liquid crystalline display or some. I mean, you should see that in your daily market stop-bys too. You should be able to see nematic phases of beans or isotropic phases of beans too. So basic idea being that the way you put things together gives you different phases. This is the same theme that keeps coming up again and again in condensed matter and in the talk. There are other kinds of phases possible too. You could have something where there is orientational order in a plane, like a nematic material, but there is also positional order in a plane, in a direction perpendicular to that plane. So for example, in the picture shown here, the atoms or the units that are the rods that are making up the system are all aligned in the same direction, but they have disordered positions in every plane. However, in the Z direction, they are ordered. So if you really think about this, in the Z direction, it's a crystal. In the XY direction, it's a plane, it's a fluid. So therefore, if you take this material and you shear it like that, it'll behave like a liquid. If you try to compress it like this, it'll behave like a solid. So now there's one more jump that we have taken. What is solid or what is liquid now depends on how you shear it. So we went into the case of anisotropy. You could have other kinds of anisotropy. For example, you could have disc-like objects, and so you could form discotic phases. Again, something that you should try when eating idlis the next time. So there are discotic phases, and so discotic phases, it's easier to shear them in a plane. It's harder to compress them in the perpendicular direction. So the point to remember from liquid crystals is that the properties of the phase, the mechanical response, electrical properties, optical properties, whatever it be, can be anisotropic because the basic units are anisotropic. Not just the individual particles, but even the properties of the entire phase. You can have more complex things, polymers, something that we all understand and appreciate, a rubber band, for instance. Having a bunch of particles, but intertwining them by connecting bonds in a linear fashion can give you something which is an extended object like a polymer. These polymer complexes can form much more complex networks. So for example, you can have linear polymers or branch polymers, and the polymers can actually form a network. Which could be cross-linked at points. And this is really rubber elasticity that comes in the play. And so we will come back to this later on. Most biological molecules are polymers. In fact, the most important biological molecule, DNA, is a polymer, as you know. One thing that comes up when you look at liquid crystalline materials and polymeric phases is the idea not only of anisotropic mechanical response, but also something that the response can show what's called viscoelastic behavior, in the sense that whether it's a solid or a liquid could depend on how fast you're shearing it. So something could be a solid at very short time scales, but if you leave it there, it can flow. I mean, this is something that we all experience again. Toothpaste, for instance, better be a solid because it should be in the toothpaste tube. I mean, it shouldn't just flow out like water. But then if it's really a solid and it's stuck inside the toothpaste tube, you wouldn't be able to brush. So you better take it out and squeeze it a little bit. That squeezing a little bit should be enough to make it flow. And so therefore it comes onto your toothbrush. So it should be a fluid for the kind of stresses that you can apply with your finger, but it shouldn't be a fluid for the kind of stresses that would automatically come from, say, thermal fluctuations. So these kinds of viscoelastic behavior is something polymers and liquid crystalline materials show. There are more complex phases, and this is where the complexity and so therefore the richness of soft matter physics comes up. So you could have molecules which are amphiphilic, in the sense that you could have systems where a part of the molecule likes water, it has a hydrophilic head, a part of the molecule does not like water, it has a hydrophobic tail. If you actually take such systems and put them in a solution, it turns out that these can actually form very complex phases. Phases that are reminiscent of things that are there in living systems. For example, you can have micelle-like phases or liposomes or bilayer sheets. And this is not something which is very complex. I mean, this is basically a resultant of simple Newtonian mechanics of a many particle system, but something that we can't actually predict until you actually do the experiment, do the simulation, or try to do some simple approximate calculation. So here's a simulation. So the simulation just shows the following, that you have a bunch of particles, which are basically dumbbells. And one of the heads of the dumbbell is repelled less by water. And the other head is repelled more by water. So whether it's attractive or repulsive, it really is a measure. So if you can repel one less and repel the other one more, it's almost the same thing as attracting here and repelling there. And you put in water and you run Newtonian dynamics. And it turns out that if you actually just watch this system over time, I hope the video is playing for you, you will be able to see these fantastic phases of micelles, vesicles, and bilayer sheets coming up. So you see a micelle-like phase coming up somewhere here. There are a bunch of bilayer sheets that are forming. So basically, bilayer sheets are configurations where the water-hating regions sort of aggregate inside, and the water-loving regions aggregate on the outside. So therefore, you reduce the energy, but in the way, you actually form a very nice bilayer structure. So this is in some sense the essential manner in which cell membranes form. So the complexity starts going up because rather than just having attractive, repulsive, you could have a system where some part of it is attractive, some part of it is repulsive, and that gives too much richer phases. So what I've been trying to do from the past few minutes is to give you a broad view of soft condensed matter. So it's basically the idea of thinking about materials that you have in your everyday life. Foams, gels, toothpaste, shampoo, sand, glass, most of food that we eat. It's basically made up of liquids or liquid crystalline materials, polymers, colloids, granular matter, and so on and so forth. Sand, for instance, something that we all play as kids, is something which is very hard. The physics of sand is very, very hard. And for this talk, living materials. So the general idea of soft matter is basically phases, collective states of systems, which are easily amenable to mechanical deformations. And typically that means the energies that you require for typical deformation should be of the order of the temperature. So basically KBT should be able to deform the system. And as we saw a glimpse of the kind of complex interactions and the resulting phases. There's a huge myriad variety. I've only touched or scratched the surface of soft matter. All right, but these are not the only kinds of phases of matter, right? I mean, there are also the quantum phases of matter. There are phases of matter where quantum effects are very important. Thermal effects hardly play much of a role. It's really the quantum effects that really dominate in controlling the kind of collective states of many particle aggregates. So for instance, you have magnets. Magnetism is essentially a quantum mechanical phenomenon. There is no magnetism in classical physics. There are superconductors or superfluids. These are materials which are macroscopic manifestations of the weird things that happen in the quantum world. We're not going to talk about them. This is what is typically referred to as hard condensed matter. This is where the quantum effects dominate compared to thermal effects. Thing to keep in mind, all this we've been discussing, we understand, and we can do some sort of a calculations, and we have a framework to do those calculations only for systems which are at thermal equilibrium, thermodynamic equilibrium. So that means, if you remember your college or school classes, the system should be in thermal equilibrium. All parts of the system should have the same temperature. It should be in mechanical equilibrium. All parts should have the same pressure. And it should also be in chemical equilibrium. All parts should have the same chemical potential. So when all these three conditions are satisfied, you say the system is in thermodynamic equilibrium. And it's only for systems in thermodynamic equilibrium that we have a very well established for many particle systems. The complexity increases when you add more interactions, more components, like we saw with the micelles and so on. But If you have a system which is not at equilibrium, we do not have a generic theory so far. What we have is a bunch of tools and techniques to work in many cases, but really there is no theory per se as in thermodynamic equilibrium. There is a microscopic theory, statistical mechanics, which tells you how to calculate all the required thermodynamic variables for a system at thermal equilibrium. In practice, the problem might be harder because you may not be able to do the integrals or the simulation might take, but then the framework is there. For a system driven out of equilibrium, you do not even have a framework, not a general framework. This is a hard problem. But that doesn't mean nature doesn't show patterns. I mean, it's our inability to calculate things for systems which are out of equilibrium. Systems which are driven or out of equilibrium do show very interesting patterns. I mean, even in the non-living world, you can see fantastic patterns. I mean, if you just take a liquid and boil it, heat it up from the bottom, you see these very interesting convection patterns that come, or Rayleigh-Benard convection patterns. Much larger problems, you could have fluids which are turbulent. I mean, being turbulent solving turbulence is one of the great unsolved problems of 19th century physics, right? We know the equations, we see the phenomena, but we don't understand how to explain it in simple words. We don't have an intuitive picture of what is going on there. It's a very hard problem left over. But then turbulent systems do actually show fantastic patterns. So this is basically what's called a Kalman vortex street, von Kalman vortex street. You should be able to see this when, for example, you might have seen pictures of air flowing past an aeroplane, which shows a bunch of vortices going behind, awesome pictures that you see on Facebook or Instagram. This can be seen at a much larger scale. So this is a satellite picture of a huge flow going past an island somewhere in the Indian Ocean. And the island is really acting like an obstacle for the fluid flow past the obstacle. And you see behind the island, these von Karman vortices coming up. So the phenomena shows patterns at fantastic length scales over the scale of the entire Earth. So that's a summary of the kind of non-living phases of non-living matter. So we could have solids, liquids, we could have pneumatic liquid crystals, smectic liquid crystals, maybe membranes, maybe liposomes, maybe micelles, or if you go into the quantum world, we have the metals or magnets, or into the turbulent world, we have the von Karman vortex streets or Rayleigh-Benard convection, and so on and so forth. I mean, this is equilibrium or non-equilibrium, but there are phenomenology. We see these patterns in the real world. So these are macroscopic aggregates. They have emergent properties. They respond to external perturbations. So these are a small sampling of the kinds of phases of non-living matter. Now I come to the main point of the talk, living matter. And if you look at living matter and you look at the phases of living matter, each creature is in some sense a phase. You get shocked. Look at the kind of phases, look at the number of phases, look at the kind of diversity of the phases in sizes, in scales, in the kind of environments they live. This is just bewildering. I mean, these are macroscopic aggregates of atoms and molecules. So they are condensed. I mean, they're not gases, they don't float away. So they are condensed phases. They interact very strongly. They need food to survive, so they are driven out of equilibrium. But they do show this pattern. So you're constantly consuming food, and there's a turnover of materials that are there in the body. Your cells die, new cells are born, atoms and molecules are recycled, but yet your form remains the same. Each creature maintains its form despite the flux of energy and material that's going through it. That's an amazing thing. So it's a sort of a non-equilibrium steady state. And the bewildering number of patterns or the bewildering number of phases of living matter is really astonishing. I was like the elephant in the room. So we were just saying solid, liquid, gas, and plasma in high school. We never thought we ourselves are a phase of matter, living matter. But then there is also a certain kind of universality that we see, a certain kind of commonality amongst all the different phases of living matter. If you take any creature on Earth, any living creature on Earth, there is a certain fundamentality, there is a certain commonality in that all living creatures, like we all know, are made up of cells, which are really the fundamental building blocks of life. And we also understand the molecule that is responsible for the hereditary characteristics, the fact that a whale begets a whale and a bacteria begets a bacteria, and so on and so forth. So the idea being that there is a certain molecule in which certain chemical chemical units can the way you arrange those chemical units can actually contain information. I mean, that's a fantastic insight. It's not just a way of arranging a chemical, but you can actually store information. It's like a hard drive that you thought about. That is a fantastic discovery. This is something which is true for all life. All life on Earth, as far as we know, is based on DNA. So there is this universality. So it goes back to the picture that I showed you earlier. Same chemical composition, but different ways of putting together gives you different phases. So you put them together in a very tight fashion, you get a solid. Very loosely, you get a gas, and somewhere in between you get a liquid. Well, I mean, that was for a one component system and also a thermal equilibrium. This is out of equilibrium. There are many components. So there are a billion different ways of putting things together. So what are the possible different ways? And some of these ways can become alive, and some of these ways can give rise to the kind of phases of matter that we can see. So here's a crash course on molecular biology. You don't need to know more. We all know that the molecule that contains the information is DNA. That's the thing that's used for the information storage part. But then the information is actually used to do something. And the machinery that does that is the toolwork of molecular biology, is the toolwork that evolution has perfected from the past 4 billion years. So DNA information is temporarily copied to an RNA. RNA comes out of the nucleus, which is then read by the ribosomes. They bring in a bunch of tRNAs. The tRNAs attach to the amino acids, and out of the ribosome pops out a protein molecule. Proteins are the workers. Proteins are the things that do all the work in the cell. They build structures in cells. They build the tracks in the cells. They build a skeleton for the cell. They polarize the cell. They make one part of the cell different from the other part. They actually make cells move. The motility of cells is really because of certain things that the proteins do. They deform the cells. When cells divide, they cut up into two pieces. They deform cells, they divide cells. And not only that, they actually make cells talk to each other. I mean, it's not in an English language or any other in human language, but it's basically certain signals that come out, signals in the form of certain protein molecules, certain small ions, and other cell has mechanisms to read and understand them. And so there's a communication that happens amongst cells. That really scales up the system fantastically, because you start getting situations where you can have really complex interacting units which are in communication with each other. Cells replicate. We'll come back to that in a minute. What are the unique features of living matter as compared to non-living matter? So we've listed out in the first part the kind of features of non-living matter: its structure, dynamics, the phases, and so on. So what are I mean, the living materials also share those phases. There are certain features which are unique to living matter. Non-living materials do not have. And so therefore, understanding the physics of living systems, physics of life, really requires you to understand these novel phases, novel features of living matter. I'll go through a bunch of slides to illustrate to you the idea of the kind of features of living matter, and then we will summarize about the unique features of living matter. The first thing is the complexity of living systems. I mean, that's just amazing. This is a picture, in fact, a hand-drawn picture by David Goodsell in this book, Machinery of Life, of possibly one of the simplest organisms that we know of, E. coli, Escherichia coli. It's a tiny bacteria. It's just about 2 microns in length and about a micron in width. And you see this cylinder-like object. That's basically the E. coli. It has a bunch of flagella, which is like its hands, which is uses to swim around. And inside that tiny little cylinder, you see a bunch of gooey things going on there. We'll go into them one by one. One thing to appreciate and understand is that since all life is based on DNA, and all life has come because of evolution, there's a lot of universality. And so this really prompted Jacob Monod to make the statement that anything that we found to be true for E. coli must also be true for elephants. So let's dive into E. coli. So we take this object and let's zoom in a bit. So if you zoom into the area near one of the flagella, you see a motor-like structure. So this big green thing. So this is the structure which is actually used to turn the flagella. The turning of the flagella allows the bacteria to propel itself forward. So we'll see a movie of propulsion of the bacteria sometime down the line. So what I want you to focus right now is on the kind of molecules that are there, the complexity of the molecules that are there, and the crowded environment that is there inside the cell. So you see a wire-like object in yellow here and in white here. That's basically the DNA of the creature. So the DNA in the bacteria is just a free-floating coil, and it sort of roams around the cell, and it's really entangled in a mass of molecules of all sizes. And we start zooming in, and you will see the various molecular biology processes happening. So again, I should have written that. This is from the book, The Machinery of Life by David Goodsell, the same pictures. So if you zoom in further, you see structures like a RNA polymerase reading out DNA and spewing out an mRNA being eaten up by a ribosome and spewing out a protein. And you zoom in further and further, and then you start seeing molecules that you probably recognize. The tiny little triangle-shaped objects here, those are water molecules. And then I have listed a bunch of things that are amino acids and sugars and small organic molecules, metal ions, phosphate ions, chloride ions, water molecules. Look at the complexity. I mean, there is structure starting from the simple water molecules, the tiny water molecules, to all the way up to the big machineries that run the system. There's a big motor which is turning the flagella. There are ribosomes which are chewing up mRNA and spitting out proteins. And there's fantastic structure going on. And at the same time, it's super crowded. How do you even get things done? Not only that, this is an object which is just a few microns in size. We discussed this, and as many of you know, at that scale, noise effects become super dominant. So thermal fluctuations are really, really high. So how is it? It's a marvelous puzzle to even appreciate how is it that the bacteria even just gets its job done. And remember, keep this in mind. This is probably one of the simplest objects in living matter. We are far, far complex. So as promised, if you actually watch a bunch of such bacteria in a solution, they move around. So if you watch the movie carefully, you will see sometimes the flagella of the bacteria open up, and then it randomly chooses some direction and then goes straight forward. So this is what's called the run and tumble motion of the bacteria. So when the flagella are turning counterclockwise as compared to the direction of motion, the bacteria swims straight. When it wants to change its direction, the flagella start turning clockwise, and this allows the bacteria to turn itself and then choose a new direction. And then again, turning the flagella counterclockwise propagates in a straight line direction. So the idea of chemotaxis is that by controlling its run and tumble motion, the bacteria can actually go close to a food source, nice to hang around and eat there, or maybe run away from a poisonous source. Get away from there, it's lethal. So this tiny bag, 2 micron by 2 micron by 1 micron bag, can actually sense what's around in the environment, respond to it, turn a motor, make decision making, and look what's around and go near the food or run away from the poison. Also share something which is fundamental to all life. It replicates. So if you watch a microscope video of bacteria, they really duplicate very, very fast. So that brings us to the next point about living matter, replication. So here's a fundamental difference between non-living matter or non-living phases, phases of non-living matter and the phases of living matter. I give you an iPhone or any phone that you like, and you give it whatever amount of energy you want. You can't go in and repair the phone or anything like that. You can supply non-directional energy. I wish the iPhone made a copy of itself. Well, the iPhone is a pretty sophisticated machine. It can sense where you are on the earth. It can communicate. Many of you are probably watching this talk on the iPhone, but yet you know it can't replicate. It's a super complex machinery that we have assembled. Can't do the basic thing that all living things do. So this doesn't happen. On the other hand, cells have no problem replicating. Just give it some energy, non-directional energy, and they spontaneously do it without the requiring of any external agency. So here's a video of 2 cells which are dividing. You see the chromosomes in red, and you see these fiber-like structures, which is basically the mitotic spindle formed of polymeric filaments called microtubules. You see the chromosomes are pulled apart and then segregated into two daughter cells, and then the two daughter cells will go on their own way. So the very fact that I said there are chromosomes and you have to pull it apart should tell you, I mean, there must be physics, there must be force there. How is it actually pulling it apart? What are the physical mechanisms of force generation? Anyway, replication is one thing. Not only that, living systems evolve and they can adapt to the surroundings. I mean, this is unlike anything that we know in non-living matter. So the basic information that is there in the DNA does change over time, called mutation, by random events. And sometimes these changes are beneficial in the sense that the changes that happen in the sequence lead to certain changes in the behavior of cells or maybe multicellular organisms. It's what we call fitness. And depending on the kind of environment that is there, a certain kind of a change in the DNA can get selected out. This is very powerful. But then life has had a lot of time. So therefore, if you really look at very, very long times, you can actually get a huge diversity of living forms. So you can get endless forms, most beautiful, and they will emerge over very long periods of time. So we have a way of classifying the kind of species that we see on Earth. And so it turns out that we have three major classification of living materials. One is the eukaryotes, including us, most creatures that we recognize, the prokaryotes, the bacteria, the ones that don't have a nuclei, and there's another class called archaea, which are closer to the eukaryotes, and there's a lot of debate going around them. So we have a way of organizing the kind of living things that we see on our planet. And they actually do this by these simple changes to the DNA structure, looking at their environment, adapting it to it, and then actually evolving over time. This is something fantastic. Like I said, the iPhone, it never makes a copy of itself. But then if the iPhone is broken, it doesn't self-repair either. But more than that, if you watch a living organism starting from a single-celled embryo, including each one of us, we start from typically a fused cell from a father and mother. That's true for most multicellular creatures. And you watch the system evolving in time. Mammals like us are hard to image and hard to do experiments on. Even mice are difficult to image. But there are plenty of model organisms which are easy to image under the microscope, and they really give you a bewildering variety of phenomena. So I want to show you a movie of a zebrafish embryo developing from a single-celled zygote. So you basically see a zygote here. This is about 0.5 millimeter in size, roughly. The most of the mass here is the yolk, which is the food for the embryo until it can fend for itself. And a bunch of cells have just about divided. So when I run the movie, you will watch a process by which this entire creature reorganizes itself into certain familiar patterns. So as you see the movie unfold, you should see several recognizable patterns. The fish is a vertebrate, so you should start seeing the vertebrate pattern. So if you put your hand back to your backbone, you will see these vertebra. So this is basically the characteristic of vertebrates. And so you see that vertebrate periodic pattern emerging spontaneously. Nobody's coming and adjusting things there. You also see the pattern of an eye coming up here. I've done the movie a couple of times. So there's no net external intervention. There's nobody's coming in and telling, put the atom here, it's not like an engineering factory where there is a certain rule, there is a certain pipeline, you design this, I'll design that. The system is doing its own design. So the product is designing itself. I mean, that's really amazing. How fun it would be if that is something which could happen to many other things. So here's the idea. Can we assemble living matter? I mean, I know I can reassemble iPhone. When I say I of course, I can't do it. But in principle, each one of us, given enough time, we can really learn. I mean, you have to learn a bunch of electronics, some machinery, circuitry, this. And so if you actually get a phone broken, as most of us do on many an occasion, we just take it to the repair guy and he repairs it. So you can reconstitute it. And even if you have made it into pieces and pieces, you can take apart the pieces. It takes longer, but you can put it back. Can you do that for a living system? So here's a question that comes up. So this is a picture from a book by Paul Alfred Weiss, Dynamics of Development, one of my favorite pictures to understand living systems. So he says the following: let's take a 6-day-old chick embryo, and that's the first image in A that you see. And let's take that embryo and let's just crush it. Crush it, don't remove anything, whatever was there inside the embryo, let it be there. Just crush it so that you sort of kill it. Then take that solution and centrifugate it. So basically put it in some centrifuge, and the centrifuge will therefore segregate all the materials according to their weight. So the heaviest ones will settle at the bottom, the lightest ones will be at the top. And so you get some state of materials. So if you notice the structure, you'll see the following. This is ordered in some sense. What is the sense? I don't know. But you all would agree it's a living thing. It has certain features, certain eyes, certain organs, certain shape. And it's in some sense, some kind of an order, which we don't understand completely yet. The crushed state is homogeneous. It's all mixed up. Every molecule is floating every other way. On the other hand, the centrifugated state is also ordered. The heavy ones at the bottom, the light ones at the top. So there is a gradient, there is a certain ordering that comes up there. Yet you all would agree with me that the last configuration, C, is not alive. I mean, it's the same set of chemicals. I did not add or remove anything. I just crushed it, I centrifugated it. I got a different way of putting together the molecules, but that's not a living thing. It's obvious to all of us. But then the first one is. So the chemical composition remained the same, but somehow the way you put things together really made the difference. This way is easy. The reverse way is impossible. So far, we don't know. So if you ask, can we assemble living matter? Not yet. So I summarize the features of living matter from a physics viewpoint. So they're very complex. I mean, there are, if you saw the E. coli pictures, you see that there are polymers, there are liquid crystalline arrays, there are small molecules, there are big molecules, there are differently shaped molecules, there are rod-like molecules. They're really, really complex. And that was one of the simplest things that we know. They replicate. They make a copy of themselves. Just give them enough energy and they just make a copy of themselves very accurately, quite accurately. They evolve and adapt. They do mistakes. There are random fluctuations that happens in the information storage. Sometimes the copying of the information also gets an error, very low, but it does happen. And over long time scales, they actually adapt. If the environment is changing, they look at that. Whichever is the fit guy for that particular environment will adapt and will win out. But if you look at an individual at a certain point of time and see how it actually builds itself, it self-organizes. There's no external agency, but this thing self-organizes. I mean, that's a remarkable thing that we don't understand. So the big picture is really the following. We have genes. They make proteins. A bunch of proteins put together make cells, and a bunch of cells put together give you tissues and organs and organisms. So in some sense, we know the interactions between the genes and the proteins. The molecular biology revolution has taught us those things. So it's an analogous picture that we have in thermodynamics, right? I mean, this is the thing that I started out at the beginning, that you have a bunch of units, you know the interactions between them to a certain degree, you put a large number of them together, and for equilibrium systems, for the simple kind of systems that we discussed earlier, there's a machinery called statistical mechanics, thermodynamics, which actually we have mastered to such an extent that we know the basic science and we've taken it to a level where we can build things that didn't exist in the world. We can build a metro car, metro train, we can build an aeroplane. So the science was built up in the 19th century, the 20th century was made really into an engineering thought. If you look at the corresponding case for living systems, living matter, genes, interactions between genes and proteins, and then there are organisms, which are really macroscopic aggregates of genes and proteins. So what is this formalism that tells us how to understand organisms starting from genes and proteins? We really lack that. I mean, there's complexity, there's something which is going out of equilibrium, they evolve, adapt, but this is a big glaring thing that is there. I mean, we understand the parts, the product is there, the product is being made from the parts, in fact, it makes itself, we don't understand how it does. So it's a very big challenge for physics. For me, this is one of the greatest challenges that will happen this century. And you should read up on Google, look at books, look at review articles. Here's a nice cartoon that appeared in New York Times last week. The article was really on the physics of sand, what makes sand soft. Looks like a simple material, but it's a pretty hard problem to understand the physics of sand. Sand sometimes flows, sand sometimes behaves like a solid. It's not thermal, temperature doesn't play much of a role, friction plays, shape matters, really complicated. So Randall Munro, who is a very nice comic artist, he designs comics at the XKCD Comics, for those of you who know. He remade this picture which actually showed the, tried to order the fields of physics ordered by difficulty. Start from classical physics, maybe relativity and quantum mechanics in general. And sand, he says, is pretty hard compared to these things. I'll venture out and say living matter is far away. So, I mean, there is a difference to be understood in terms of the difficulty. So the first three regimes, we know we think we know the fundamental laws, and they're really borne out over the past century. For sand, we don't know the fundamental laws at all. For living matter, we're really, really struggling. There's a big, big, big opening that's coming up to understand living matter as physical matter. Okay. Okay, I've gone for about an hour. So the last part, I was going to tell you a little bit about the kind of things that I do. I'll go over quickly. It might be a bit too technical, which is fine. I don't intend you to get a full picture. And if you have questions, you can ask me later on. So one can broadly think about the kind of physical approaches to living matter and classify them into three categories. This is my picture. This is not something standard. So everyone will have his or her own picture. So one can look at cell and developmental biology. How do cells get made from a bunch of molecules, or how do organisms, multicellular organisms, get made from a bunch of cells? You could look at a special kind of cells, the neurons. They really form a very strongly interacting condensed matter systems. So strongly interacting that a bunch of neurons is telling that a bunch of neurons is a complicated system. I hope you got that. A bunch of neurons, my head, is telling a bunch of neurons is a very complicated system. It's a very self-referential thing. There's also the ecology and evolution aspects. When you put large number of creatures, interacting creatures, on long time scales, evolutionary aspects come into play. Fantastic physics opens up. Very broad, so one can't study all of them. So I focus my efforts on cell and developmental biology. I'll just give you a brief glimpse of the kind of things I do. So I look at development. I look at development of multicellular organisms. I'm really fascinated by how organisms shape, how they start from an embryo, few cells, how they divide, how they actually make their body parts, how they know their head and the tail, how they know their front and the back, how do they make their internal organs, and so on. So this is again a different video of the same creature, zebrafish. Starting from a single zygote, you start seeing the formation of the vertebrae, the eye pattern comes up, and in just about a day or so, you see a nice fish coming up, and even the pigment pattern starts appearing. So there's a general scheme that happens for multicellular organism development. So the general scheme is something that most multicellular creatures follow. There are specializations, there are special cases here and there, but this is a general thing that follows for most multicellular organisms. The egg and the sperm interact with each other, they get fertilized, they form what's called the zygote, something that we have all gone through. The zygote undergoes a set of divisions wherein each cell, the big cell divides into a bunch of cells, tiny, tiny cells. The mass is conserved, but the size of each cell goes down. It's called cleavage. The cells then rearrange themselves in a process called gastrulation. I'll tell you about gastrulation in a minute. Then they specialize. Certain cells become eye cells, certain cells become nose cells, whatever. Certain cells become neurons, certain cells become cardiac muscle, and so on and so forth. And that finally gives rise to the creature. So this is all in words. We still don't have a clear picture of how things work. So the phenomenon of gastrulation is something that you all should think about. So when a creature forms, it's basically a big ball of cells, right? So it's really a solid topology. When you think of yourself or any creature for that matter, you'll see you're basically like a rubber tube. There's an inside and there's an outside. So for people who understand mathematics, it's what's called a topology change. So living things actually undergo a topology change during their gastrulation phase. Louis Wolpert actually made a statement that it's neither your birth, nor your marriage, nor your death that's the most important thing in your life. It's gastrulation. Because you really define what's inside you and what's outside you during that phase. So I look at several model organisms. I collaborate with experimental groups. For example, this is a C. elegans zygote. This is a creature for which a certain process I've worked on extensively. So it turns out that this creature is more or less transparent. So you can see through the organs inside. So you can actually catch hold of one of the embryos which has been fertilized, and you can put it under a microscope and watch it develop. Okay, I don't know why the video did not play. Is the video playing? Probably not. All right, doesn't matter. There are physical problems in developmental biology that I'm really keen to understand. So these are problems that involve how to make different kinds of cells. For example, the idea of differentiation, how to shape up the cells, establishing axis, the head-tail axis, the front-back axis, the left-right axis, and so on. And then the problem of pattern formation. So I'll just show you a couple of videos that actually show you these patterns. Okay, the videos are not playing. I don't know why. Okay, here it comes. So for example, the fruit fly gets patterned by making certain segmentation patterns, which really has a nice correspondence to the adult organs. So the very early in the development, a certain chemical lays out the axis of the embryo, which the mother helps. And then a series of chemical reactions cascade to define the different segmentation patterns. So many people have tried to understand this using physical arguments. For example, there are models called the positional information model. Let me not go over them for reasons of time. There's a fantastic model called the Turing model, which really Alan Turing proposed in the early 50s. This is a model based on just simple chemistry, interacting chemicals, moving around by simple diffusion. And he showed that if you look at the mathematics of these equations, it turns out that the system can become unstable to small perturbations, and it can develop spontaneous patterns. So these are the analogs of the non-equilibrium patterns that I told you about very early on. But it turns out that people long speculated that Turing patterns must be there in biology, but it's only the past decade or so people have actually found experimentally the molecules that actually do involved in Turing patterns, the kind of reactions that they undergo, and shown that there is indeed a Turing pattern sitting here. Each one of you has a Turing pattern. Your digitation pattern is really a Turing pattern. The fact that you have 5 fingers, maybe some other creatures have so many different fingers, is really a Turing pattern. But then the thing that drives me a lot is really trying to understand the following question. If you look at a developing embryo, how can it be that it's only a bunch of chemical interactions that's doing the job? I mean, you really look at the organism developing, there are biochemical signaling patterns, sure, but there are also shape patterns. The thing is changing in shape. It's like if I give you a piece of clay and ask you to mold it into an elephant shape, you need to push out something, pull something, stretch something. So you need to do force, you need to do mechanics. Where does that come from? So there really must be a crosstalk between biochemical signaling patterns and shape patterns. And this is what really drives me. I look at mechanical forces, the kind of mechanics that comes up in fluid mechanics or elasticity theory, for instance. And I try to understand how those mechanical forces crosstalk with biochemistry and geometry. This is something that D.R.C. Thompson had speculated more than 100 years ago. We didn't know about the chemicals or the molecules that actually do the job, but he really speculated that the laws of physics and chemistry must drive the understanding of living organisms. So let me skip some details. So there is a certain structure called the cytoskeleton, which is really the structure responsible for generating forces in all living cells and tissues that we know. And this certain physical theories have been developed from the past 2 decades, which is really trying to look at this structure as a non-equilibrium driven matter. And the kind of patterns that come up in these can be modeled by appealing to the kind of physics that we do in elasticity theory or fluid dynamics. So the point is not to scare you with the equations. The point is to just show you it's not all words, and there is rigorous mathematics behind this. And one can actually compute things, calculate things, and like in good old science, you can actually go back and check with experiments. And that's what I want to leave you with one particular problem of mine. So the problem that I had told you about is that cell divisions many a times during development most all times need to establish the head-tail axis. Cells become polar. Turns out that this polarity pattern establishment in the C. elegans zygote is one such mechanochemical pattern. It's a pattern where mechanics does a crosstalk with biochemistry. So this is a problem that I worked on, and we have been able to actually show that the mechanics, biochemistry crosstalk can actually explain the molecular concentrations, just like in a physics experiment. You do physics experiments in your 12th standard, you take a pendulum, you put it here and there, you measure some period, some formula somebody has derived, and you check some mathematical formula against a physical system. The claim is biological systems are no different. If you can calculate things quite well, and if you can measure things quite well, you can actually do the physics of living systems. All right, so here's the summary. So I hope I have convinced you that life is soft, it's active, and it's a complex matter. Not the colloquial terms, it's a soft condensed matter system. It's an active soft condensed matter system in the sense that it's a non-equilibrium driven system. It's a complex material. There are various kinds of structures, myriad kind of interactions, long range of length and time scales that interact with each other. This idea of looking at the physics of living systems is very highly interdisciplinary. It presents some really challenging problems in physics and mathematics. And I urge you to look up on Google, look up search on Wikipedia or wherever you want. It's poised to be one of the most dominant research themes in the 21st century. There are many groups around the world and in India too who are working on these things. So here's an invitation. If you really love challenging problems, hard problems in physics and mathematics, but that could be as fundamental as explaining life, you should come to this area. But I want to leave you with a bunch of things that you can explore further. Textbooks are not there yet. This is a really hard research field, but there are many semi-popular articles which give you some ideas about the kind of things that I talked to you on soft matter. I recommend the first row for semi-popular accounts, The Many Phases of Matter by Venkataraman or Soft Matter by Piazza, the book by Goodsell that I referred to many a times. I very strongly recommend the book by Ian Stewart, which really talks about the mathematics of life and really documents the kind of revolutions that have happened in biology, starting from the invention of the microscope, the cell theory, the genetics, evolution, DNA, and he says the sixth revolution is going to be mathematics. So by that he means really that biological experiments will get more and more quantitative. They already are. So more and more quantitative data, which means numbers. So you need mathematics to understand those numbers. The bottom row are more technical. They're really textbooks, introductory textbooks with some little bit of a knowledge of undergraduate or 12th level physics and mathematics. One can really grasp them. They really give you a foray into really nice ideas in physics of living systems. All right, so I'll stop there. That's my group last summer before the pandemic hit. And I'm supported by Biotechnology Department, Government of India. I have a Max Planck partner group, which is where I really collaborate with my experimental groups. And ICTS also supports this probably weird area at the interface of physics and biology and mathematics. All right, I'll stop there and take some questions if you have. Thank you.
Thank you, Vijay sir. It was a very interesting and interactive talk. Actually, most of us enjoyed, and in our YouTube also we have lots of comments saying the talk was very interesting and the things were very relevant to the topic, and the talk is going in a very good phase, and also really very happy about it. And yes, I too agree it personally. The things which the flow of your talk from the phases of matter to the structures to the phases of from interaction to different phases and then the quantum phases, and then the most interesting one for me was the movement from the non-living to the living part. So that was all very fantastic and very interesting. So to go with the first question in the first part of the slides, in the phases of interaction, we have a question from Swayu Rav. He is asking about, can you please explain physically the different peaks in the pair distribution of liquids?
Yeah, so it turns out, maybe I can go to that slide. Yeah, so it turns out that liquids are things, like we discussed in the previous slide, which don't have so much of a kinetic energy that they just come, bump, and go off. They actually explore these attractive well, right? So therefore, if two liquid molecules come close by, they can momentarily get trapped in the well. So therefore, the probability of finding the two things at this distance goes up. That's the first peak. But then if two things are bound, the second one can come in and they can actually form a triplet. So which means the next probable distance is twice the diameter. So that's the second peak, and so on and so forth. So this is basically the idea of shells that you would form. So one molecule, a bunch of molecules around it, that gives you the first peak. A second shell of molecules around it gives you the second peak. But then as you go further and further away, the chances of you getting a organized structure really goes down. And so therefore the peaks vanish in amplitude. I hope that made sense.
Okay, perfect, sir. So next, most of them I see they are very interested about knowing what is that which is creating this living things on Earth. The derivation from the non-living to the living. So most of them are asking about the interactions, the fundamental interactions which is happening and which can happen to turn non-living matter to living.
So, I mean, that is the big question. We do not know that, right? So if you take a protein inside a cell and you compare it to a protein that maybe you can make it up in a chemistry lab, you can't make out the difference. So in terms of the proteins, in terms of the molecules, the interactions, it's essentially the same thing that you would measure in a lab. So the idea of something being alive, like I said in the very first slide, is not a property of the individual units or the interactions. It's really a property of the collective whole. And what is that property? Well, that is a big question. I mean, we don't know that. I mean, if we knew that, we could probably reconstitute life. We don't know that. I mean, my aim in this talk was not to give you answers, but to just provoke you to think that there are these big questions unanswered. And though we understand these tiny details, we don't understand the big picture yet. So the answer is, we don't know.
Yes, if that was really answerable, we could have really created lives today on Earth. So that's still question. It's a God matter. So, okay, going further, we have a question from Anandi Mathur asking, how would you explain the functioning of isolated biological molecules as in a PCR?
Well, the function in the sense that they are just doing their chemistry, right? I don't know, if you catch hold of a molecule, would you call it alive? Probably not. I mean, DNA by itself is probably not alive, right? DNA plus a bunch of machinery surrounding it gives it certain properties that can replicate, can evolve, can sense, can self-organize, and so on. So somehow, again, it's the same question. The individual molecules, we can take them out in isolation, we can do their chemistry, we can do their physics, but it's really this living state is something that comes up when you put a bunch of them together. How is it that they are being put? We don't know.
Yeah, exactly. In PCR, we are just getting the replica of the DNA or RNA material, what we are actually using as sample. And then whatever replica we get, we try to encode them to what proteins they encode. And from the protein, we just get to know the functionality. That's all until now. We all have known about the isolation of the biological materials. So going further, so few people are interested with the video what you showed, sir, the zygote video. So from Zenith Afreen is asking, is it possible to rearrange the cells during the cleavage of zygote and observe the result as and then the developing of organs happen? Is it physically possible?
Yeah, people have done these experiments. You should look up, Google the Spemann-Mangold organizer. So it turns out that you can actually take a developing creature, cut it a piece here, glue it somewhere here. You can make all kinds of weird organisms. So the creatures do develop for some time. There are these ideas that there are specialized regions which have information about the creature. There are certain signals that come about which tell you which is the head, which is the tail, and so on and so forth. So one can actually do these experiments. These are routinely done in the laboratory. Many a times they survive. Most of the times, sometime down the line, the change becomes lethal. But there are abnormalities, and this is a routine thing. Embryology cut and paste is something just been done from the past 100 years.
Yeah. Okay. So one person is interested about your study, sir. Shashank is asking about what kind of mathematics you use in your study.
Yeah. So I am a physicist who looks at the statistical properties of living systems. So therefore, I look at statistical physics, statistical mechanics. By definition, living things are driven by certain energy. So therefore, non-equilibrium statistical mechanics. Equilibrium is also helpful in certain points. I look at coarse-grained descriptions, which means rather than looking at individual molecules, individual interactions between molecules, so on, I look at coarse-grained pictures, much like you do in thermodynamics or fluid dynamics. So I write down partial differential equations. So the kind of mathematics is really looking at the partial differential equations for densities, for elastic deformations, for fluid flow rates, and so on. I try to see how those equations can get coupled to the stresses or the forces generated from biochemical transduction of energy to force, which is what is done by the motors in your system. And the kind of thing that I want to do, I'm doing and want to do for the next few years, is to really look at how this couples to shape. I mean, elasticity obviously tells you that if there's elastic force, the material will deform. So you do see deformations in the embryo. Somehow it's self-organized by certain gene expression patterns, generating certain biochemical patterns, generating certain force patterns, which is leading to certain shape patterns. And the shape patterns will, so there's a constant feedback between shape, biochemistry, mechanics. So I would like to sit in this kind of, so to answer the question about mathematics, statistical mechanics, stochastic processes, partial differential equations, differential geometry, and biochemistry.
Okay, perfect. So thank you. So next question is from Manjunath. They're asking about does the size of the attracting states get maximized along with the correlations during a transition? If this is true, what is the explanation from the physics relating to the attractor sizes and the correlations?
I don't know which attractor. I presume in the fluid part.
Most probably fluid only, sir. They are talking about the correlations getting maximized between the interactions.
Yeah, okay. So the kind of quantity that we calculate, the pair distribution function, turns out it's actually a correlation function too. So it's really related to the correlations of the density field of the molecules that you're looking at. So the fact that you have this attractive potential between the atoms at short ranges, long ranges, really creates these enhanced density correlations. And the density correlations are what we see as the liquid-like structure. I hope that answers.
Yep. Yes, sir, exactly. So next question is from Abhishek Srivatsa. He's asking about does spherical harmonics that we study in quantum mechanics play any role in mitosis or gastrulations?
Yes, it does. Spherical harmonics basically represent the kind of deviations of a shape from a sphere, for instance. And I use that regularly in my studies because you start typically from a sphere-like shape. Well, I mean, favorite of physicists, right? Because that's the only thing that we can solve in generality. So we start from sphere and we look at deformations of the sphere. And so therefore, we do expansions in spherical harmonics. So spherical harmonics, you should really think of as the eigenfunctions of the Laplace operator. It's not really related to quantum mechanics per se.
Next.
Ask questions themselves.
Next.
I hope there are two.
Yes, sir. We have lots of questions here. And next question is about what is the difference between positional model and turning model?
Turing model. So in terms of the physics, they are more or less identical. I went through that quickly. I do appreciate that. Somewhere here. So the idea here is that this is what's called the positional information model. The picture really came about by looking at certain patterns that you see in tissues where a certain chemical is secreted by a bunch of cells, a single cell or a bunch of cells, and then the chemical sort of diffuses around in the extracellular region. By looking at the concentration level of that chemical, other cells, the non-secreting cells, can actually figure out how far away from the secreting cell they are. So in a sense that it's simple physics of diffusion and simple degradation by absorption of the cell, absorption of the molecule into the cell. And you can actually show by solving this simple differential equation that the profile is going to be an exponential. People have actually measured this profile in the experiments. For example, the patterning of the front and the back of the Drosophila wing disc is controlled by a certain protein called DPP, decaplant-apregic, and you can actually measure its concentration profile, and the profile really follows this mathematical relation. So this idea of positional information is that you can get information about what to differentiate into by measuring the position of your location or your position with respect to some source. So the position carries information. But then this is a pattern which is sort of is non-autonomous in the sense that there is a certain source at a certain point which is secreting something, and that is driving the entire pattern. Turing models, on the other hand, are what are called autonomous systems. These are systems where a bunch of chemicals, at least two of them, if they are interacting with each other, so Turing showed the mathematics of the chemical interactions, the specific details of the chemical interaction hardly matter. The thing that matters is that one of the molecules should be an activator, the other molecule should be an inhibitor. And if these molecules satisfy certain conditions on their diffusivity, one can show mathematically that a uniform state becomes spontaneously unstable to fluctuations and can give rise to periodic patterns. So that's the time development that's being shown here. There's a uniform state, a small fluctuation that happens. There's a positive feedback that happens from activator-inhibitor kinetics coupled with diffusion, and that can actually lead to stable periodic patterns. So to answer it in one sentence, periodic Turing patterns are spontaneous instabilities. They are autonomous patterns. Positional information patterns are driven by a certain source. They're non-autonomous.
Okay, so moving further, there's one question from Ekta. She's asking about if we can answer the fundamental questions of living organisms, living matter, is it possible to be answered with artificial intelligence and machine learning?
Yeah, surely. Biology is so complex. It needs everybody. If people say this is biology, does not need physicists, they're going to miss out. It's so complex. And if you think about it, it's probably the fundamental problem that we have in science. And so people who do artificial intelligence, machine learning techniques, computational methods, everybody comes in. They could be at the level of trying to sort of decipher the patterns in the experiments by using artificial learning or machine learning techniques, or maybe deeper, trying to understand how neurons are connected to each other, how a network of neurons really comes up from talking to each other and does what it does by thinking of neural networks. I mean, the name itself tells you neural networks really came up as a toy model for thinking about interacting neurons. So now you've taken that to machine learning, deep learning, and forgotten neuron. That's where it really came from. Of course, it can really be used, and there are plenty of people using that. It's a fantastic tool.
Okay. Next question is about, do you agree with the that there is evidence of magnetic properties in living matter?
There are, but not so significant. There might be some subtle effects. I'm not very aware of them. For example, there is some quantum effects also speculated in avian navigation, some single triplet state. I don't know how well established they are. So very minute effects. For example, it's known that many birds use the Earth's magnetic field as navigation tools to go north or to go south, and to do is basically using that like a GPS map. How they do that, and is it really the magnetic field? I don't know. I would rather not comment on that. I don't know.
Exactly. Okay. Going further, we have a small idea from Rishikesh, and he is saying that there is an idea among some that life itself is a shortcut to increasing entropy in the universe at the much faster rate compared to non-living matter, and hence any matter would assemble itself over the long periods of time to constitute living matter. Do you agree with this, sir?
He's
talking about entropy. The faster the rate of entropy, it is going to convert non-living to living. Does that give you any kind of idea, or do you agree with it?
The point is that I mean, there's a lot of debate and there's a lot of discussion about the role of the second law of thermodynamics in living systems. And there are plenty of books and papers that you should refer to. They don't violate the second law of thermodynamics. There's no conflict there. They're somehow using certain patterns, certain fluctuations, certain short time scale things to actually self-organize. So we don't understand that yet. So maybe just to reiterate in a general context, like some wise person told me once, living systems operate not despite the laws of physics, but because of the laws of physics. So therefore, they don't violate anything there. They're using some other tricks and tools which we don't understand yet.
Correct. We really have that question in mind. So going further, we have a question from Manmeet Kaur. He is asking about in nematic phase, what is the reason behind same orientation of molecules? Why doesn't entropy destroy it?
Yeah, good question. So it turns out that it's actually entropy that's making them, it's a combination of internal energy and entropy that is actually doing this job. So what you should really do is to do this experiment with the beams, that's all. So if you scatter the beams far away in a very low density system, you can put them in any random orientation, it hardly matters. But you just take the system and compress it with your hands from far away. Don't even touch each and every beam. Just compress the edges of the system, just push it. You'll automatically find the beams will just align. So it's not something where entropy is being, I mean, you're not respecting the law of entropy increase or something like that. So it's basically a case where at that energy, at that temperature, what matters is the lowest free energy state. And if you remember, the free energy is a combination of the internal energy and the entropy. So you could go down in free energy by either going down in internal energy or by going up in entropy. And so the fact that this is a low free energy, the minimal free energy state at this temperature really tells you that you're actually increasing the entropy.
I think that answers his question. So one more question from Kishore Nori. How do we approach the physics of life or dynamics of what is happening inside a virus and its interaction with bacteria?
Yeah, very relevant question to the current situation. Viruses are, I don't know much about viruses, so take it with a pinch of salt. Viruses are sort of on the borderline between what is living and what is non-living. Viruses cannot replicate themselves. They need a host cell. They hijack the machinery of the host cell. They use all the machines and parts sitting in the host cell and make copies of themselves. Now, there is a good amount of physics that people have studied about the formation of the viral coat, the lot of engineering mechanics in terms of elasticity theory. But I think the problem is complex enough about how the interactions of the virus with the bacteria or any other host cell comes up, how it hijacks its machinery. And I don't think we understand things very well yet. It's a very simple molecule, but we don't understand.
Yes. So next, we have a lot of question about life, about gene, about what do you say, how about increasing the mortality rate of an organism. All these questions are there. So commenting from a non-physical background, from a biological background, yes, gene mutations happen, gene interactions happen. There's a lot of what do you say, gene combination happening in humans when there is an embryo getting formed. Okay, so in that stage, whatever physics we can go and apply there, whatever permutation and combination you're talking about, we're applying over there. Yes, but still, even today, siblings don't look alike. Even identical twins don't have the same genetic makeup, and mimicking life is still a question. Still, life is a miracle, and we really need to agree with that point. So for those who are questioning about the gene interactions, we'll have to just wind up with that simple thing. One more thing about physics, computational physicists. What sort of tools, computational tools or mathematical tools one should learn to be able to do physics in life?
I mean, I think I did answer the kind of mathematics that I do, but in
Tools,
general,
he's asking for tools.
yeah, in general, I mean, you should be very good in differential equations, in stochastic processes, probability theory, Markov chains, queuing theory, geometry, topology, and so on and so forth. In terms of the computational tools, I don't know what do you mean by the tools. If it's a programming language, it's up to you. You can use whichever one. There's nothing to recommend. One is good or the other. But I don't know what for example, many people use machine learning tools, if that's a tool to think about, to understand many patterns in living systems. That's one tool. That's one computational tool that I can think of. I use a bunch of tools to solve the differential equations, partial differential equations that I encounter. There are libraries for linear algebra tools. There are libraries for solving algebraic equations and so on. But this is getting into the integrity trace. Maybe there was a bigger level question which I did not get.
Actually, he's like asking about where to start with. Okay, if we are dealing with physics of life, and what kind of biology should he start with? If it's physics of life, and what kind of tools we need to go about. So that was his question.
Okay, I mean, you do need to learn biology. There's no doubt. There's no escaping that. I mean, I think it was said in the introduction, I did not like biology the way it was taught, so I left it very soon. I did not like the mugging up part of the thing. The physics and mathematics really attracted me. But then people showed that there is a lot of physics and mathematics in biology too. But how much biology should you know? Well, you can take one or two courses in some basic biology institutes or your college, or read up some books on these things. So not much. It's without angering anybody or without making arrogant remarks. It's easier to learn biology. I think it's a little harder to learn mathematics and physics.
Okay, with that note, the last question for the session, sir, it's from Jaidev Subramaniam. So he's asking about when a biological system succumbs to decay, does the system's emergent properties or complexities and entropy play a role in this?
Yes. When a system decays, it reaches thermodynamic equilibrium. And we know the physics of thermodynamic equilibrium very well. So the upshot is, if you are at thermodynamic equilibrium, you're dead. And that we know very well. It's really the state where you're not at thermodynamic equilibrium that we have a lot of problems.
Okay, sir. So wonderful session, sir. Now I hand over the session to our MC Ranjita to carry forward.
Thank you, Archana ma'am. Thank you, Vijay sir. Gratitude is one of the most beautiful way to express all that's in your heart. By two words, thank you. Now I call upon Professor Hemawati, Department of Biotechnology, MLAC, to propose a vote of thanks. Hema ma'am, over to you.
Thank you, Archana, and thank you, Ranjita. Coming to the concluding remark, it gives me, it gives me immense pleasure to deliver the word of thanks. The highlight of today's webinar, Dr. Vijaykumar Krishnamurthy. It gives me great, immense pleasure, to thank you on this occasion where you have delivered a beautiful lecture, your talk, okay, which kept almost the audience engrossed throughout your session. You have given a beautiful interplay between the phases of matter, quantum dynamics, and their relevance in our day-to-day life. You have also shown how these matters play a very important role in the existence of living and non-living matter on Earth. Thank you so much, sir. I would now like to thank the technical team behind the success of this webinar, the team members of ICTS, Anupam Ghosh, Kavyashri, and Naveen for your valuable efforts in planning and execution of this webinar. On behalf of principal, management, heads of the department of MLAC, I express my heartfelt gratitude to the speaker and the team of ICTS. I also extend my gratitude to Dr. Babita, head of the Department of Biotechnology, and our technical team, Archana Preeta and Ms. Ranjita, for their efforts in putting up this webinar. I'm thankful to the principal, Dr. Shashikala, and management of MLAC for their support and encouragement in organizing this webinar. Last but not the least, the audience for showing their interest in this and registering in large number. We have participants from various institutes and organizations, Bangalore Central University, IISc, SER, and then Christ University, BITS Pilani Institute, etc. In fact, we have had an overwhelming response both in the Zoom platform and on YouTube. Thank you again for your interest. Hope you have had a great learning experience. Thank you all. Looking forward for a similar response in our future endeavors. Thank you all again. Thank you, sir. Thank you, ICTS team, for a very wonderful organization of this webinar. Thank you so much.
Thank you. Thanks, everyone. Thanks for coming.
Thank you, one and all. With this, we come to the end of the session. Ladies and gentlemen, it's a kind request to give your valuable feedback. The feedback link is shared in the chat box. Kindly go through the link and give your valuable feedback. Now I request all the participants to raise for the national anthem. With that, we come to the end of the session. Once again, thank you, one and all. Thank you, one and all. Have a great day. With this, we come to an end of the session.